that magical land called the cloud. All right, so we have first problem. For a man to cross a lake to a point directly east of his cabin, he must set a course 6 degrees south of due east so as to compensate for a current that flows to the northeast, specifically 30 degrees north of due east. Right? So at any point you start drawing the diagram, but you might want to consider the situation also. If the man's boat travels 20 miles an hour in still water, what's the rate of the current to the nearest integer? What's the resultant velocity of the boat? Right. So let's get our diagram going here. The point across the lake is directly east of the cabin. Right. So let's get east going here. Of course, let me get my line draw tool on. So a little off. All right. So got our 2 points. This is the cabin. Yeah, the location that we're aiming for is just a point across the lake, so I'll just say point. All right, so he's going to set a course 6 degrees south of due east. All right, I don't know how long that's going to be, so I'll just eyeball it. Yeah. And then make adjustments down the line. So 6 degrees south of due east. Right? Then we're compensating. He's aiming his boat in that direction in order to compensate for a current that's going 30 degrees north of due east. So let me actually move this down a little bit. So yeah, scaling isn't really that important, but just for personal satisfaction, I'll just make it look like a steeper angle. And that's really all I'm looking for. So 20 degrees north of due east. Okay. Now, his boat travels 20 miles an hour in still water. So that would be, if there was no current, that would be the rate that the boat would travel. Now we want to know what is the rate of the current. Well, the current is the thing that's going to the north. So that's going to be this upward vector. All right, so this is the current. All right, and we're looking for that rate. All right, so we could define it any way we want. We can call it vector C for current. Right, so what we're looking for is, and it says the rate to the nearest integer. So we're looking for a magnitude. So this is current, we'll call it C. So that means that we're trying to find the magnitude of C. All right, so that's our goal for the problem. Just try to clean that up a little bit. And then what is the resultant velocity of the boat? Well, the resultant would be the velocity that the boat actually traveled at. So that's going to be this. I'll call it the boat. And we'll call that B. So we're looking for the resultant velocity, so we're looking for the magnitude of B. All right, so we have vector, that vector B is going to have a particular magnitude, and that's our objective, to figure that out. All right, so I want to make a complete diagram out of this. So I want to name that last vector something reasonable, south of east. Yeah, that vector going downward is the direction that he's aiming his boat, but that's not where his boat is actually going to end up going. So I'll say direction boat is aimed. All right, so I guess that'll make that either D or A, I guess. A for aimed, sounds good. All right. So now what I want to do is I want to piece this together and create the parallelogram. I like the parallelogram approach, so that's the way I'm going to handle it. right? So in order to do that, I'm gonna trim it up a little bit. So I'm gonna take my upward facing vector and reproduce it on the lower end. But in doing so, I'm gonna trim it because I don't need nearly this much, right? So I'm gonna chop off a fair bit of it. So bring it down. I think that's probably good enough. So I get rid of this and replace it with a more reasonably sized one. All right, same idea for the lower one. Trim it down, copy it up, and paste it in. Okay, so it's a little bit off. Just pretend. All right, so we got our two vectors. We're looking for a resultant, so that's a vector sum, right? So I'm going to need some angles here, and then we need our relationship. So now I say that I need angles, and you look at it and say, oh, the angles are given to you. Yeah, kind of, sort of. They're given to us, but not in the way that we would want, because what we want is an angle that deviates from the 0 degree mark. So I'll put this, so east is going to represent 0 degrees. So that first angle is fine, that's 20 degrees. But that second angle, I'm not going to say that that's 6 degrees. I'm going to say that that's, and I'm going to go around, 360 minus 6, so 354 degrees. All right, so that's a slightly different take on it, but it gets the job done. All right. So what I'm going to do is I'm going to set up my vectors. So I have my vector C as magnitude of C. It's an unknown. Well, there's some extra information here that we're going to be able to make use of, but I'm going to pretend that I don't know it just yet. All right. So we have vector C. Let me use my writing tool here. Multiplied by cosine of 20 degrees, comma sine of 20 degrees. All right, that's the component form of vector C.
Is it 30 degrees?
Oh, thank you. Oh, wait. I read it off my diagram, but my diagram was wrong. Thank you. Yeah, the 20 is the speed. We'll get to that in a minute. All right, I could actually just kind of move this over a little bit. A is going to be the magnitude of A, cosine 354.
Professor, is that a 60 or a 6 degrees?
Oh, that's 6.
Okay, the degree thing just looked really like a 0.
Oh, gotcha. Yes, 6 degrees. All right, and so ultimately we're looking for the vector sum in order to find that resultant vector B, because B is going to be equal to, and I'll just make a note of it up top here, B is equal to A plus C. So I can add these two vectors together, and that'll get me my vector B, which is ultimately what I'm looking for, all right? In a manner of speaking anyway. But we do have some information, some other information that we can work on, right? And that is that the boat ultimately ends up moving in the direction of 0 degrees, right? So that's seen, and I'm just going to move this over a little bit so I have more room. So when I'm finding my vector sum, I can say B, which is the sum of A and C. I can start looking at all these other values, but I can also just simply say B cosine 0 degrees, sine of 0 degrees. All right, so we have something that we can set our equation equal to, right? Because that's what the resultant is, it's the sum. So we can work this a piece at a time. All right, but we also have that 20 miles an hour that we can work with. All right, well, we know that that's not going to be the magnitude of C because that's the rate of speed of the current. It's not going to be the magnitude of B because that's the ultimate speed that the boat ended up traveling at, right? And they ask us for that. They ask us for the resultant velocity. So the only thing that could be is A. And so what it says in still water, well, the water is not still. So what do? Well, we imagine there is no current. This would be the speed that the boat would be able to travel at. So the best we can do is take the boat and aim it 6 degrees south of east at that rate of 20 miles an hour and hope that it straightens out to that resultant vector going along the 0 degree vector, so we use the term, right? So I can pop that in. I can pop it in now, I can pop it in later, it doesn't make a difference, all right? But I am gonna do some resizing here because I'm writing big. All right, so what I can do, if I'm getting my sum here, is I can just add the different components. I can take the magnitude of C, distribute it to each term within the component form of the vector. The magnitude of A, same deal, and the magnitude of B, same deal, all right? So I'll write that step out over here. That's, and in that process, we'll do the math, you know, because cosine of 30, sine of 30 are things that we could figure out, right? So this would become the vector of magnitude of C times radical 3 over 2, comma, magnitude of C times 1/2. Going off the board here. Oh, you know what? Let me erase that for a sec. I want to change my pen size and also move some things around. Just going to tiny put it there. All right. So we're looking at magnitude of C times radical 3 over 2, comma, magnitude of C times 1/2. We do the same thing with the A, but we also happen to know, like I said before, we also know that A is equal to 20 miles an hour. So I can bring that in. Now, suggestion, I think you're better off leaving it as cosine of 354. You know, cosine of 30, sine of 30, those were easy to work with. But this, I mean, you're going to get a disgusting decimal. And unless you want to include a disgusting decimal, and you don't, you're probably better off just leaving it as the cosine of 354 and the sine of 354. So we're going to say 20 cosine, sorry. Comma, sine, 20 sine of 354 degrees. And the really, really nice case is the actual sum because it goes off in the 0 direction. When you distribute, cosine of 0 is equal to 1. So magnitude of B times 1 is magnitude of B. Sine of 0 is 0. Magnitude of B times 0 is 0. All right. And so what we can do is establish equality here based off of these two relationships. I can work these separately from these. All right, so the next step would be to establish those equations because I know that the magnitude of C times radical 3 over 2 plus 20 cosine 354 degrees should be equal to the magnitude of B. Which is great if only I knew what the magnitude of C was. If I had that, then I'd be in good shape. And then you look at the second equation and you say, oh, I actually do have that, or at least I will in a second. So magnitude of C times 1/2 plus 20 times the sine of 354 degrees is equal to 0. Right? So it ends up being a system of equations that you can solve fairly easily. Okay? And that's because our second equation only has the one variable in it. Right? So that's going to make life a lot easier. Right? I'm going to clean it up a little bit by multiplying everything by 2. Right? And so it would be magnitude of C plus 40 sine 354 degrees is equal to 0, which in turn means that the magnitude of C is equal to negative 40 sine of 354 degrees. Now it's a velocity, so velocity should have magnitude and direction, right? So it's covering, we've got the direction part of it covered with the sine function and the cosine function pointing the way, but in terms of the magnitude, we actually have to crunch these numbers in order to see what's up, right? So I get the old Desmos calculator out. Oh, eventually, I suppose. All right, so I'm going to type in negative 40 times the sine of 354 degrees. So I got to refresh my memory on this. You got to put the degree symbol in.
Desmos knows. That's the right answer.
Oh, that's Desmos knows?
Yeah, but 33 is the right answer. Negative
Gotcha.
33 is the right.
The issue is it should be a positive number because the sine of 354 is fourth quadrant value. So a negative times a negative should be a positive. So there's definitely something wrong here. Let me do it the old-fashioned way. Yeah. I just did I'll figure out the degree form of it in a few minutes. But I just converted it to radians so that Desmos would understand. All right, so just pop a pi over 180 right onto it and you get it. Yeah, this is a much more reasonable value because this is the rate of speed, the velocity rate for the current. If the current was going at 30 something miles an hour, I don't see how the boat is getting across the water at all, right? But for a current to be going around 4.2 miles per hour, I think it was miles per hour, yeah, then that seems a lot more reasonable. So this is approximately, it's the nearest integer, so 4 miles per hour. Okay, so now we have our C value, which is great. I just need to pop that in and use that to come up with the B value, but that's direct substitution. I just want the truer value to be plugged in. So we know that this entry here is really what C is, the magnitude of C. So I'm going to pop that in there and crunch out the values using, again, Desmos. All right, so I'm going to type in, I'll just type it again. So negative 40 sine of 354. Again, I'm just putting it as pi over 180. Then plus 20 cosine Same deal, 354 pi over 180. All right, and that should do it. We're looking at approximately, again, nearest integer, so approximately 24 miles per hour.
Do you have to multiply it by radical 3 over 2?
Yeah, I was gonna ask.
Oh, I missed the radical 3 over 2. Ah. There you are. So radical 3 divided by 2 multiplied by. Okay, so now we're good. Still, surprisingly, still ends up being 24 miles an hour. So I guess I would have got lucky there, but yeah. All right, so this is an example of the boat getting an assist from the current. Okay, the current is, it's not going to contribute all of its velocity. Well, actually, in this case, it seems like it is. It won't always contribute all of its velocity toward the efforts of the boat driver, but in this case, it seems like it is. Right? But yeah, it's a system of equations, because once you get the setup taken care of, the setup taken care of.
This might be a dumb question. Why is it negative radical 3 over 2?
Why is it negative radical 3? Oh, it's radical 3 over 2. I just tucked it between the negative and the 40 that I put in for magnitude of C.
Ah, okay.
So number 3, fairly similar in terms of the scenario. Tabitha took a journey on a blimp due north. She traveled at 45 miles per hour by setting a course 17 degrees west of due north to compensate for a wind that was blowing 50 degrees east of due north. Draw a diagram used to find the actual velocity of this wind-blown blimp to the nearest integer as it traveled due north. Right? So, it's just wordy. But once you kind of get down to business, you start understanding that, okay, there's a process involved here. Right? So she traveled 45 miles an hour by setting a course 17 degrees west of due north. Right? So I'm going to get west and north involved. Oh, man, I cannot. All right, so that's, well, I don't think I need to label that part of it because west and north are pretty obvious. All right, 17 degrees west of due north. So just pop it like that. Label it up, 17 degrees. To compensate for a wind, compensate for a wind that was blowing 50 degrees east of due north. All right, so I'm going to establish 50 degrees east, just a quick ballpark estimate. East of due north, all right? So there's my north. That's the benchmark. 17 west of it, 50 degrees east of it, all right? So she actually traveled 45 miles an hour, right? She did that in the northern direction. We don't get to that till later in the question when it says find the actual velocity. Well, she aimed at 45 miles an hour. We don't get till later in the question that the resultant is actually due north, right? So it turns out that I don't need as much of this. I hardly needed any of it. So this is my resultant vector. We need to figure out that velocity. I'll call it n for north. Well, I'll just label it as n. And keep it simple. W and E, west and east. Not due west or due east, but just in the westerly and easterly directions. All right. So I have those values. Now, she aimed it 45 miles an hour, 17 degrees west of due north. So that's telling me that the magnitude of W is going to equal 45 miles per hour. All right. They don't say anything about the velocity of the wind. They just tell us the direction of the wind, right? So it looks like it's the same kind of situation where we don't have all the details, but we have enough to get started, right? So we know what east looks like. I'll label that. (0 degrees). So we're going to our 3 angles here. We got this one, and this one. All right, so the angle at E, I'll just label it at the bottom here. Angle, the measure of angle E is equal to 40 degrees because it's coming off of the x-axis. So not 50 degrees away from the x-axis, it's 50 degrees away from the y-axis. All right. North, the magnitude or the measure of angle N is 90 degrees, that's the right angle. And then the westerly one, that's going to be 107. All right. So then we can go to our setup because we know by experience and now also, or well, by definition, but now also by experience, that this should be a vector sum situation, right? So like I said, I'm just going to tailor, like I said before, I should say, I'm going to tailor my diagram to fit the situation here, like right there, I guess. I'll do it slightly differently this time. Look at this out of here. Okay, so this will be my new E. This, bring this in. Then we trim this down. Oops, took too much. Close enough, I think, as I proceed to like edit it. Although this time I'm just trying to move the end. So got the diagram. It's part of the requirements of the question, so I wanted to make sure I had that done. I can just move that over. Now I'll take care of my sums. Right, so we know that we have E, that should be green. It's going to be the magnitude of E times the cosine of 40 degrees of the sine of 40. We got a W, so the magnitude of W. We actually know that's 45, so I'm not going to beat around the bush here. I'll just chuck that right in. So cosine 107, sine of 107. And then that should be equal to, with the vector sum, just can't get it to go straight now. Whatever. That's going to be equal to N, which has an unknown magnitude. We're looking at cosine of 90, sine of 90. All right. And so we can jump right to, you start getting the hang of this, you can start streamlining the process. If you know that you're going to distribute just to add and create equations, you can just do that all in one shot. So magnitude of E cosine 40 plus 45 cosine 107 is going to be equal to the magnitude of N times 0, so really just 0. So I'll just make that a 0. All right, cosine of 90 is equal to 0. Then magnitude of E, sine 40 plus 45 sine 107 is going to be equal to the magnitude of n times 1, so just the magnitude of n. At this point, it's really just the same kind of problem because we're solving for E first. Magnitude of E is going to be equal to, subtract and divide, negative 45 cosine 107 divided by cosine of 40. And then that value gets popped into the other equation to give you the value of n. Right, so we crunch those numbers and we have our answer. You know, with the appropriate rounding and the appropriate rounding and units. I lost the word there for a second. So get my Desmos out. No, let me just do it real quick before I forget. So degrees. Desmos. Oh, that's stupid. Jeez. There's a setting. I mean, it makes sense that there's a setting. It's just, it doesn't make sense that I didn't think that there would be a setting. 45 cosine 107. So now we're looking at something much more reasonable. Divided by cosine 40. Oops. So E is going to be approximately nearest integer. So yeah, we're looking for n ultimately. So we didn't really need this, but I'll put it anyway. About 17 miles per hour. Okay, so that's the wind velocity. Again, we didn't need that, but it's there, so why not? Right, so I want to build off of this answer. So what I'll do is I'll hit that little whatchamacallit jammy there, the gear, and duplicate. Hit done. Oh wait, sorry. Duplicate, and then tap on it so I can edit, and type in my sine of 40. Plus 45 sine 107. And so we're looking at about approximately 54 miles per hour. All right, and again, ultimately, this is the answer we're looking for, not the other thing. The other thing I did just because it's force of habit, but the real answer that we're looking for here is the 54 miles per hour. All right, which should make some sense. She traveled, or she aimed her blimp. I don't know if a single person could own a blimp, but she aimed her blimp and then got an assist from the wind. All right, that wind is producing 17 miles an hour worth of extra speed. Right, so she's not getting all of that because the wind is not at her back, you know, like 100% at her back. She's only getting a certain percentage of the wind, but that percent that she's getting amounts to an extra, a little boost of 9 miles per hour. Right, so she's not getting all of the 17 miles an hour that the wind is producing. She's only getting some of it, but that sum is pretty substantial. And you know, this is you know, a rudimentary or elementary calculation behind, if you think of like when you're on a plane and you hit the jet stream, you know, you're going east to west versus west to east across the country. And it's like, oh, we're going to get in an hour early. You know, it's like, whoa, how come it takes an hour less time to travel one direction as opposed to the other? And that's because of the assist that you're getting from the wind. That's part of the fun. Right. Number 4, a 50-pound weight is hung by a cable so that the two portions of the cable make angles of 30 and 60 degrees respectively with the horizontal. Find the magnitudes of the two forces of tension T1 and T2 if in the cables if the resultant force acting on the object is 0. Okay? So this is a better diagram than I could produce, but what I'm going to do is I'm going to streamline it. I'm going to break it down even simpler. So we have an angle. Let me do this all in black. Angle created by the two vectors coming together, and then we're also heading downtown here. We got that opposing force. All right. Now, I'm going to establish that the x-axis and the y-axis, I can put them anywhere I want. For convenience, I'm going to put it right at the intersection. All right. So I'm going to create a vertical going through. All right. So this is what my graph would look like. I want to make it as much like a coordinate set of coordinate axes as possible. You do need a little knowledge of geometry. So I'm creating a line parallel here with the line connecting, or basically the ceiling. And so if two parallel lines are cut by a transversal, the alternate interior angles are congruent. So that makes this guy over here 60 degrees. And this one over here would be 30 degrees. All right. Now, we're concerned when we're dealing with these vector type problems, we're concerned with the angle from 0. So I know that this guy is going to be 60 degrees. That's the easy part. This one is going to be 30 degrees short of 180. So that's going to be 150 degrees. The last one, 3/4 of a turn around the circle, is going to be 270 degrees. All right. Now, it tells us that the magnitude of the forces of tension T1 and T2 in the cables, or that's what we're looking for, and the resultant force acting on the object is equal to 0. All right, so there's a lot of stuff going on here. Now, we're going to call one of these T1 and the other T2. It doesn't make a difference which one we call. Right? We just have the angles. One of the cables has tension 1, and the other of the cables has tension 2. So T1 and T2. Right? That's going to correspond with a particular magnitude. So we can start working on that part of it. Just create some room. So I can say that T1 is equal to the magnitude of T1 times the cosine of 150 comma the sine of 150. And then the same idea for T2 except 60 degrees. All right, now the vector sum here should be that last vector that we know has an angle of 270 degrees. We just don't know anything else about it. I mean, we do, it's just not stated obviously and apparently. Right? So they told us here that the resultant force acting on the object is equal to 0. Right? So that part's taken care of. The resultant force is equal to 0. So that's talking about a vector sum, right? But the issue is this doesn't look like any diagram that we've created, right? So what I want to do is I want to draw it again, but this time without all of the fluff, right? So write down the brass tacks here. So let me get rid of this. Let me get rid of this. And let me get rid of all the angles. All right, so basically I just got a y, right? So what we're ending up with is a relationship that tells us if we were to find the resultant of these two vectors, so these two going off in the upward direction, we would create our parallelogram. I'm just freehanding it here. Terrible job freehanding it. I'm reversing course and not freehanding it, for the record. I'm just going to do it the right way. All right, so we have this resultant vector. Now, this is a product of the way I drew it, but this resultant vector is the same length, or it should be the same length as the vector going in the downward direction. All right, which I'll make that purple. All right. And the reason why is they have to balance each other out, right? In order for the tension in the cable, so T1 and T2, I'm bringing some labels back, to amount to equal 0, this value here, which I'll call R, has to balance out with the other magnitude. So I'll call this negative R, all right? They have to balance each other out. Otherwise, there would be some kind of movement, all right? So what ends up being the case is if you establish that the object is stationary, it's not going anywhere, normally T1 and T2 would have a resultant that produces some sort of movement in that positive direction. But because there is no movement, whatever's happening in the negative direction must be serving to balance out using the exact opposite relationship. It must serve to balance out or cancel out the positive resultant vector. All right. Now, you may look at this and say, well, you didn't put any negatives in there. Where's this negative R you're talking about? Well, one, negative 0 is 0. So that wouldn't help. The negative comes up in the coordinate values. So cosine 270, sine of 270, as opposed to cosine and sine of 90, that's where you get the negation. All right. So I want this resulting value T1, T2, T1 plus T2 to be equal to 0. All right. So after, long story short. So we got that. Now I can set up my system of equations. I'm looking at T1 cosine of 150, right? It's 30-degree reference angle in the second quadrant. So negative radical 3 over 2 plus T2 cosine of 60 is 1/2. And that should be equal to 0 because the cosine of 270 is equal to 0. All right. You can clean this up a little bit. I wouldn't go too crazy just yet because the next computation might change your thinking. So T1 times 1/2 sine of 150, 30-degree reference angle in the second quadrant, plus T2 sine of 60 is radical 3 over 2 equals sine of 270, yeah, -1, that's great, but it's multiplied by a resultant value of 0, so it's still going to be equal to 0. All right, so we have a system of equations, 2 equations with 2 variables. You can pick and choose your battles here. Most people tend to want to go with substitution.
Is that T1 or T2? No.
It's T1 and T2 in both equations.
Okay.
Now we don't have the luxury like in the last couple of problems of having one equation with one variable. That makes things a whole lot nicer. So we got a little bit more work ahead of us. But one thing we could do off the bat is multiply everything by 2, like across the board. Makes life a little bit easier. That just jumped on me, I don't know why. So 2, oh, no. The whole point was to get rid of the denominators. So negative radical 3 times the magnitude of T1 plus magnitude of T2 is going to be equal to 0. And then T1 plus radical 3 magnitude of T2 also equal to 0. All right, that gives us the luxury of being able to solve one of the equations for one of the variables and then go from there. All right, so I'll just do it with the second one because it's right in front of me. So we have T1 is equal to negative radical 3 T2. So we could do a direct substitution if I now know that T1 is equal to negative radical 3 T2. I can pop that information in and go from there. So we'd be looking at, let's bring this down. Negative radical 3 times negative radical 3 is going to be just a 3. So 3 T2 plus T2 is equal to 0. All right, I screwed something up. I don't know where I went wrong though. This is about to give me a 0 and that's not right. I don't know. Pause the recording while I troubleshoot this. Resume recording. I got to face the music here. It is what it is. Yeah, the resultant value, it's 50. It's going to zero out. It's going to balance itself out, but that doesn't mean it's going to be equal to 0. So apologies, but that's going to change our second equation. The first one is fine. That should be a negative 50 over here. I guess we'll do that in purple. The first one's fine because cosine 270 is 0 anyhow. So that's okay. So my first equation's good. On the bottom, doubling it was still an idea that worked. But the second equation, where we got the that relationship, that should be different. So let's make that adjustment. This should be negative 50. So I'll just tack on a minus 50 here. And then when we do our substitution, it's still
Minus 50 or minus 100?
Sorry?
Is it minus 50 or minus 100?
Minus 50. Oh, now it's minus 100. Thank you. Now we're getting into the snowball effect here where I make one mistake and now I'm compounding it. So 100, so doubled it, minus 100. All right, well that's something. Anyway, so I'm going to replace, but then this is going to be a little bit more elaborate. So let me clean that up. So negative radical 3 multiplied by this whole jammy plus T2 is going to be equal to 0. All right, so got a little bit of work to do. It's not going to be quite as clean as I had hoped, but clean and wrong is never going to be the best option. So rather be a little messy and but then be correct. All right, so distributing, I'm looking at 3 T2 plus 100 radical 3 plus another T2 equals 0. All right, so we're going to have 4 T2. I'm going to bring this over, equals negative 100 rad 3. And so T2 is going to be equal to negative 25 root 3 for quality 3. All right, the negative's talking about direction. I'll get to that in a sec. But before I do that, we can crank out the value of T1. So T1.
Where did the 4 come from?
Oh, coefficient, understood coefficient of T2 over here is a 1.
You just combined like terms.
Exactly.
Okay, thank you.
No problem. So we have T1 is going to be equal to, so we're working off of this equation now. All right, so T1 is going to be equal to radical 3 times negative 25 radical 3 minus 100. All right, so that's going to give me a negative 25. Because radical 3 times radical 3, 3 times 25 is 75. So 75 minus 100, negative 25. All right, so then all I'd have to do at this point is formally state what my final answer would be. All right, and this is where I'm going to talk about the whole negative number thing, because it's like, well, a negative weight, that doesn't seem to make sense. Right, so T1 and T2, we're going to go with the absolute value of these measures, because this is 25 pounds. And T2, it said round to the nearest tenth, I think. So I'm just going to pop that in, 25 rad 3. We're talking 43.3. It all has to do with the orientation or the relationship between these values and the weight. Because I put the weight in as a positive number, right? So that weight, I put it in as 50 pounds, all right? 50 pounds in the downward direction, but still 50 pounds, right? When I put it in as a positive number, I established that going down is a positive movement, all right? So going in the downward direction is a positive movement. So any movement that's in the upward direction would necessarily have to be the opposite direction of what I've established as the positive, which is downward, right? So in this case, if I had gone and put negative 50 as downward direction, 50 pounds, then these numbers would have come up as positive. And you know, we're still only caring about the absolute, so it doesn't make a difference. But it's worth noting because it has been a point of concern in the past. And this looks ugly, so I get rid of it. All right.
The
So
negative sign means that it will always be positive.